In 1929, Edwin Hubble published a paper that shook the world. He discovered that the universe was expanding. Ever since, we've known that space is getting bigger, but now astronomers think it might be getting blue. And if they're right, our entire understanding of the cosmos could be turned on its head. As far back as 1954, some scientists have suspected that the universe may be filled with strange, dark energy. Most astronomers today think this so-called dark energy makes up around 3/4 of everything in space. And most of that dark energy is thought to be a mysterious force called the cosmological constant, denoted by the Greek letter lambda. But there's one thing that doesn't quite add up about the cosmological constant. According to Einstein's equations, it should change over time, but observations show no such change. This has led many astronomers to hypothesize that the cosmological constant isn't constant at all. Instead, it could be changing in ways that we haven't detected yet. There are several ways a changing lambda could explain what we see as an accelerating expansion of the universe, which would mean that distant galaxies would appear to be moving away from us more quickly than expected. It also means that those galaxies should be getting bluer, because as an object moves away from us, its light gets stretched, shifting toward the red end of the spectrum. The farther away a galaxy is, the faster it appears to be receding, and the more redshifted it should be. But observations show that distant galaxies aren't just redshifted, they're actually blue-shifted, meaning they're shifting toward the blue end of the spectrum, indicating that they're moving toward us rather than away. If the universe is truly expanding, then these galaxies should be moving away from us and getting redshifted, not blue-shifted. And while random fluctuations in matter distribution could cause some small-scale blue shifting, the effect we see is too large to be explained in this way. This observation was first noted in 2018 when scientists analyzed data from the Dark Energy Survey, which had been looking for signs of dark energy by measuring the rate at which the universe was expanding. That's when they noticed that the distant galaxies in their survey weren't as redshifted as expected. In other words, they were blue-shifted, but they could think of no physical mechanism to explain why that might be. However, 2 years later, in 2020, a different group of researchers proposed a solution. They hypothesized that the blue shift could be explained by a change in the cosmological constant. These two groups' results seem at odds with each other, but they don't have to be. The key is how exactly we measure the rate at which the universe is expanding. There are 2 main methods astronomers use to measure this rate. One involves looking at what's called the cosmic microwave background, or CMB. This is the radiation left over from the Big Bang. By studying the tiny temperature variations in the CMB, astronomers can work out how matter was moving around when the universe was very young, which gives them information about how it's moving today. The other method involves looking at distant supernovae. As these explode, they briefly shine extremely brightly, allowing us to measure their distance. By combining this distance measurement with how fast they appear to be moving away from us, astronomers can work out the rate at which the universe is expanding. The first group of researchers found that when they looked at the CMB, they couldn't see any evidence of the accelerating expansion, but when they measured the supernova, they did. The second group saw the opposite. They found evidence of an accelerating expansion when they looked at the CMB, but not when they studied the supernova. This apparent contradiction might just be an error, like misinterpreting a graph or making a mistake with the data analysis, or it could be a sign that something is seriously amiss. Either the scientists didn't understand how the universe works, perhaps the laws of physics are wrong, or the data they collected was misinterpreted. To figure out what's going on, let's first look at the data itself. To do that, we need to talk about a phenomenon called gravitational lensing. As light travels through space, it bends around massive objects, distorting and magnifying the light from objects that lie behind them. Gravitational lensing is useful for astronomers because it allows them to study otherwise invisible galaxies and helps them measure things in space, including the rate at which the universe is expanding. When light gets distorted by a gravitational field, it changes speed. Light that passes close to a massive object will be slowed down by its gravity, and light that passes far away will go almost straight through, barely losing any speed. This change in speed causes the light to refract, just like when you put a straw in a glass of water and it looks bent. When light refracts, it disperses into a rainbow of colors due to a phenomenon called dispersion. Different colors of light bend at slightly different angles. So when light from a distant source passes through a gravitational field, it arrives at Earth not as a single point, but as a series of points spread out along a line. The exact pattern depends on the strength and shape of the gravitational field, which depends on the mass distribution of the object during the bending. This distortion allows astronomers to calculate the mass of the object, giving them another tool for measuring the properties of things in space. But gravitational lensing doesn't always work as expected. For example, in some cases, the distorted light forms multiple images of the same object. This happens when a massive object lines up perfectly between Earth and a more distant object. In this case, the gravitational field of the foreground object creates multiple paths that the light can take to reach us. And if these paths are long enough, the light doesn't have time to combine again, creating multiple images. This is called strong gravitational lensing, and it happens fairly often. Weak gravitational lensing, where the light is only slightly distorted, is even more common. And here's where things start to get weird. In 2020, that team of astronomers who claimed to see evidence of a blue shift in the universe used data from the Dark Energy Survey, which looked at an eighth of the sky. The survey used a technique called photometric redshift to determine how far away galaxies were. Photometric redshifting involves looking at how much each galaxy is redshifted based on its color. Because there's a relationship between how redshifted an object is and how far away it is, this allows astronomers to calculate the distance to a galaxy just by looking at its color. This technique isn't perfect, though. It can't tell the difference between two galaxies that are very far away but redshifted and one that is close but blue shifted. In other words, it can't tell whether the galaxy is receding from us or approaching us. It turns out that the majority of the galaxies used in the 2020 study overlap with ones that had been previously identified as gravitationally lensed by another survey called the Canada-France-Hawaii Telescope Lensing Survey, or CFLENS. Now, if you recall, there are two possible explanations for the apparent blue shift. One is that the universe really is blue shifting. If that's the case, then the photometric redshifting method should underestimate the distances to these galaxies because it will incorrectly identify them as being closer to us than they actually are. And if this is true, then the gravitational lensing survey should overestimate their distances because it will incorrectly assume that they are further away than they really are. Basically, the two surveys should give completely different distance measurements for the same galaxies. Now, in 2022, another group of astronomers took a deep dive into this issue, collecting data on a subset of the galaxies used in the original study. They wanted to find out if the 2020 results were correct. They knew that if they were, then the two surveys' measurements of the same galaxies should match up pretty well. If they didn't match up, then the 2020 results were likely wrong. Luckily, they had a way to rule out the possibility that the discrepancy was caused by an error in the data. That's because when studying these galaxies, they could use both the photometric redshift and the gravitational lensing to measure the distance to each one. If the discrepancies were caused by an error, then the two measurements should be similar. What they found was the exact opposite of what they'd expect if the universe was blue shifting. Their measurements agreed perfectly with the 2020 study, but only within the margin of error. But when you look at the actual numbers, the two sets of data don't match up as well as you'd expect if the 2020 results were right. Not only that, but the 2020 results were based on a statistical analysis of hundreds of galaxies, which should have produced a much smaller margin of error. All this suggests that the 2020 result was likely an error. However, this doesn't necessarily mean that the universe isn't blue shifted. There are other surveys that have claimed to detect the same thing. Unfortunately, none of them have been able to rule out the possibility of an error like the 2020 study did. So the question remains, is space really getting bluer? We just don't know the answer yet. Maybe one day soon we'll discover that the universe does indeed blue shift, in which case we'll need to completely reimagine our understanding of reality. Or maybe we'll find that the blue shift is just a trick of the light. Regardless, one thing is certain, we live in an amazing universe. If you like learning about all of this, then you'll love our space and physics courses. Space is an introduction to the solar system, the interstellar medium, stars, galaxies, and cosmology. You'll learn about planets, moons, asteroids, comets, and more. And the course covers how stars form and die, the evolution of galaxies, and the origin of the universe. Physics is an introduction to classical mechanics, electricity, magnetism, waves, and optics. You'll learn about motion, forces, energy, momentum, gravity, electric charges, circuits, light, and more. Both courses offer a beginner-friendly introduction to fascinating topics and are taught by experienced and award-winning teachers.